Today's high-speed serial buses necessitate the need to accurately measure transmitter performance. As data rates increase, the effects of the measurement circuit, for example, cables, fixtures, and probes, have a larger impact on overall margins. Measuring the true depth performance requires removing the effects of the measurement circuit to observe the signal as if the probe, fixtures, or cables were not in the signal path. In addition to loss, the reflection caused by impedance mismatch must also be removed when considering the effects of the measurement circuit. Compensating for the effects of the measurement circuit can be quickly done using Serial Data Link Analysis Visualizer for Tektronix real-time oscilloscopes. In this video, we will show how quickly a cable can be de-embedded from the signal path of a PCI Express Gen 3 signal running at 8 gigabits per second and how to validate that the de-embedding has been done correctly. SDLA is broken up into two circuits, the measurement and simulation circuit. The measurement circuit is issued to describe the physical test connection to the device under test. This includes cables, probes, and fixtures. In order to fully describe the interaction of the test setup with the DUT, the measurement circuit must also describe the transmitter and receiver profiles, which include package models and impedance models. The first step is to obtain a model of the circuit to be de-embedded. In this case, we have measured S-parameter data that represents the cable model. I have created a math function of my differential signal, so I use the signal input of SDLA and assign the input to SDLA to be math1. I now need to describe the path model as part of the measurement circuit. By clicking on the DeEmbed block in SDLA, I am presented with an 8-block cascade. By clicking on the first block, I am presented with different options on how to describe my model. Since I have a single 2-port S-parameter model for each leg of the cable, I choose the file selection and select 2-port under the model. I can now simply select the S-parameter file for each leg of the cable by clicking the Browse button. Once the S-parameter files have been loaded, I can use the SDLA plotting capabilities to verify the models. Each S-parameter is plotted in an individual window, allowing me to quickly verify the reflection and transmission terms of my model. Since my cable is well controlled, I expect that loss will be the main contributing factor. Based on the plot, I would expect less than 1 dB of the loss at the fundamental frequency of 4 GHz. The next step is to decide where to observe the signal. In this case, I want to look at the signal before and after de-embedding, so I will enable TP2, which will show me the signal with the cable removed and the loading effects of the simulated circuit. I have assumed a 50 ohm nominal impedance for my transmitter and receiver. Had I wanted to observe the signal with the loading effects of the cable, I would want to observe the signal at TP1. I simply click on TP2 and assign TP2 to Math2. I then select the Apply button on the main SDLA menu to create the transfer function to apply to the signal at TP2. Once the model has been applied, I can quickly verify my results by looking at the eye diagram before and after de-embedding by selecting the Analyze button. I can then customize my results by adding additional measurements, for example, eye height at my source eye and eye height at TP2, and recalculate my results. The resulting improvement of my eye was roughly 80 millivolts. This video has demonstrated how using SDLA Visualizer can be used in order to measure the true depth performance.